What fraction of the volume of an iceberg, density 917 kilograms per meters cubed, would be visible if the iceberg floats in the ocean um, and in a river? When salt water freezes to form ice, the salt is excluded, so an iceberg could provide fresh water to a community.
So the water has different density depending on their state, the matter state, as well as uh, con the material contained inside of the water too. So the iceberg is basically the ice state. They have density slightly less than the liquid state, uh, and if the water has different content like salt, then also they change the density too. So depending on the density of the water, you may end up with a different fraction of volume submerged into the water. So um, let's start with some basic configuration to simplify this circumstance. So now you have the water in ambient water around the iceberg. So you have iceberg submerged into this water. The total volume of this water could be the volume of iceberg, and the part submerged into this water could be VF. That is non-visible portion. So the amount of the non-visible portion pretty much depend on how that ambient liquid, how much density the ambient liquid actually has. So that this EF could be volume replaced by the fraction of iceberg under the water. So the fractional ratio could be formulated with the total volume of iceberg and the fractional volume of the water replaced by the iceberg. So that should be like this. Okay. So that actually fractional ratio between the total volume and the non-visual portion submerged into the water. So if you just re-express this one, then that should be 1 minus ratio between the fractional volume and total volume. So that's a simple relationship between the two volumes, depending on the densities of those two material. So in order to iceberg the floating on the water, the gravitational force or weight should be same as the buoyant force, obviously. So that should be Fg, which is mass of the iceberg times G, and that should be same as upward force out of the fluid, the liquid of the water. That should be mf of G times G. So from that, the mi portion, the mass itself, is same as the submerged portion of this iceberg. So obviously the mass is density times volume. So if you re-express this relationship with the mass density and the volume of each fraction of the iceberg, then that should be rho I times VI, the density of iceberg times total volume of iceberg, and the density of fraction replaced by this iceberg times volume of submerged portion. So if you rearrange this relationship, then that should be the ratio of volume between those two portion is same as the ratio of density. So let me just rewrite it. low I, and low F, right? You move that this one to right hand side, and this one to this one to the this side, then you should be able to get this relationship. And using this relationship, you can solve the problem. So the fraction number A is the what is that? The what fraction of volume of iceberg would be invisible if iceberg floats in the ocean, salty water. So density is slightly higher than pure water. So if you replace that, then fractional ratio, as I show you before, this fractional ratio is 1 minus low iceberg or low F, right? That's the F. So that's 1 minus iceberg density is 917 kilogram per cubic meter. So that's 19 kilogram per cubic meter divided by salty water. That is the 1024 kilogram per cubic meter. So the 1024 kilogram per cubic meter. So that is about 0.1, which is 10%. So you have probably 10% floating over the surface of this water if this iceberg actually just submerged into the salty water in the ocean. Okay.
Mhm.
You can find similar fractional ratio for liver. The liver case, the water itself is pure water. There's no salt mixed into the water, so your density is 1,000. Can you just tell me how much fractional ratio you may have out of that condition? So now that is one minus low I and low F. That this one should be the density of the fresh water.
8.3%.
8.3%. Oh, probably you have to multiply 100 if you want to express it in percentage unit. If you multiply 100,
Yeah. Because
not 8,
as a
so
decimal, I got 0.083.
0.83, right?
Mm-hmm.
Oh, yeah, yeah, right. So 0.83, yeah, has multiplied by 100. So, okay, 8.3%. Okay, that's it. Right. Do you understand this problem and the solutions too?
Mm-hmm.
Okay, then let's move on. All right. Can you read this problem?
Yeah.
Number 4.
A wood block, mass 3.67 kilograms, density 600 kilograms per meters cubed, is fitted with lead density 1.14 times 10 to the power of 4 kilograms per meters cubed, so that it floats in water with 0.9 of its volume submerged. Find the lead mass if the lead is fitted to the block's top and bottom.
So the wood block is fitted with lead. So that those two material have different density. So the mass might be different too. And they are just thrown into the water, and they supposed to float in water with the zero point 0.9 of its volume submerged. So like 90% of the mixed material block is just submerged into the water. And in that case, we gotta find the lead mass if the lead is fitted to the block's top portion and the bottom portion, right? So for number A, uh, in order to float on the surface in the water, then buoyant force should be balanced with gravity. So that's buoyant force of this portion of the water replaced by the this wood block is low W V I G, right? So that is Vi is the point 0.9 wood, right? That is portion of submerged into the water.
Mhm.
So if you replace that, then it should be point 0.9 low of water times volume of wood times G. So now, um, that the when the floating, then buoyant force equal to the weight of wood and lead, right? So now this one should be re-expressed with the uh, the mass relation, mass and density, mass density relation. Then that should be zero point 0.9 times density of water times G, and volume V, the volume of the wood, the we express with this mass wood divided by the density of wood. You understand why, how that the volume we express with this relation, right?
Yeah.
Just the mass is just density times volume.
Mhm.
So now the that's number one. The second, that should be same as the gravity of the wood and the lead. So that gravitational force out of that block mixed by the wood and the lead should be mg, which is actually m wood plus m lead times g. That is downward force by gravity. That should be equal to this buoyant force, right? So that's make 90% portion of this wood block submerged into the water, but 10% floating over the surface of the water. So with that relationship, zero point 0.9 low water, density of water times G times M wood divided by low density of wood equals M wood plus mass of the wood and the mass of the lead times G. Can you maybe rearrange this formula in terms of the mass of red? Can you re-express mass of red by rearranging this formula then?
Mhm.
The next step is pretty straightforward, so that this conversion of this equation in terms of this mass of lead is the key. So you got to just uh, rearrange it to find the expression of the mass of the lead. And next step is to plug the numbers into the formula.
I got 0.9 times density of water, parentheses, mass of wood over mass or over density of wood minus mass of wood equals mass of lead.
So zero point 0.9 times, and then what?
Density of water.
Water, and then
Um, parentheses, mass of wood over density of wood,
uh-huh.
minus mass of wood.
Okay, perfect. So that is formula out of the one above this equation, right? Then next step is just plug the number. So the density of the water is, how much is that? It doesn't have the number, but usually we already know the density of water, of fresh water, 1,000 kilogram per meter cube to the
Mhm.
cube, right? Cubic meter. And mass of the wood, where is it? As is 3.67 kilogram. And density of the wood is the 600 kilogram per meter to the cube. And mass of the wood, the same thing. That is 3.67 kilogram, right? Can you
Mhm.
plug the number and tell me how much mass
Yeah.
you got?
I got 1.84 kilograms.
Okay, that's good. Yep, that's correct. And the number B, we gotta find that the last mass if the lead is fitted to the block's bottom. So you have to add additional term due to the lead, because a lead is fitted to the bottom of the block. I mean bottom, yeah, but the blocks of the bottom, right? So you should have additional term by the adding that the water that is replaced by the lead block. So basically buoyant force portion in number A, only if you take into account top part of this block, then that was 0.9 low water of the density of water times G M wood, and the low wood. But here you need the, because you have water submerged, and now you have the lead fit in the bottom. So you have that amount of water should be taken into account, the buoyant force. Okay, because in the previously that top part had red that part was not part of the buoyant force, but now your lead is down to the bottom of the block, so you have to additionally just add that buoyant that water replaced by the lead uh, into the buoyant force. So here that is the mass water times G. So that is, let me change the color. So this term with additional term due to the fact that the lead is fitted to the block's bottom. All right.
Mhm.
So in order to derive the formula out of this Beijing equation, you have to convert the mass of the water with the mass of red and the mass of the actually volume of the water. So basically, now this one, let me just convert that the expression. So the mass of red, obviously the density of lead times volume of red, and the mass of water is also density of water. Water times volume of water in that portion bottom of that block. And from that, this volume of red is mass of red over density of red, and this one is volume of water, the same as the mass of water and the density of water. So I told you this second additional term added because that volume of lead, the volume of water submerged into the bottom of the block is replaced by that lead, right? So basically this volume of lead inside of this block and volume of water replaced by the lead must be same. Understand what I'm saying?
Yeah.
So two volume must be same because they're submerged into the water, and the water portion 100% replaced by the lead. So that volume itself must be same. So this volume, this part of the volume, is the expression of water, they must be same. So that is mass lead over the density of lead, same as mass of water as density of water. Okay, now, because of that, mass of the water could be expressed with the mass of the lead and the density of water and lead. So that is low water over low lead times mass lead. Got it? So if you plug back into this formula, then let me just clean it up and then remove some of this page. Okay, hold on. Right, delete of that. So now then, the equation itself is just changed to the 0.9 low W G M wood over low wood times, plus low W and low lead times mass lead G. That is buoyant force, right? That buoyant force, as I said, it should be same as the gravity, the downward force out of the gravity on this block. So that should be same as mass lead plus mass wood times G. Okay, so you have complete equation so that the buoyant force, this one is same as gravity. Okay, so Everything is same except that additional term, second term. So you should be able to draw the formula again. Re-summarize to drive formula for mass of red. Can you do that?
Mhm.
Pretty straightforward, just like the equation, I mean the problem A. Have you found it?
Not yet.
Okay.
I got mass of lead is 0.9 times density of water,
Mhm.
parentheses,
Mhm.
mass of wood over density of wood,
Mhm.
minus mass of wood,
Mhm.
times times parentheses density of lead over density
Mhm.
of lead minus density of water.
Well, maybe that same answer, but just the that a little bit different in the way of the expressing the formula. But I think it is probably the same answer. But let me give you how to drive the formula. That's actually pretty straightforward. Look, see that this one is if you put the G inside of bracket, then that should be M le G plus M would G, right?
Mhm.
And you move this second term into the right hand side and move this one to I mean that would M would G should be moved to the left hand side of this equation, and this second term should be also moved to right hand side of this equation. So that rearrange then point should be point zero low WG times M would low would minus M would G equals M lead G minus low W low lead times M lead G, right? So you just shuffle around. So if you combine the terms in the right hand side, then that should be 1 minus low W over the low lead times G M lead, right?
Mhm.
So if you just divide both sides of this equation by the 1 minus low W over low lead times G, then M lead should be 0.9 low W. Hold on. Okay, let me just rewrite it. Low WG M would and low would minus M would G over 1 minus low W over low lead times G, but the G can be canceled out of numerator and denominator. So that should be same as 0.9 low W M would over low would minus M would over 1 minus low W or low lead. Okay?
Mhm.
Now, next step, you plug the numbers into this formula. So, as you know, this numerator, you don't have to actually do the math because you already answer for numerator. you already calculate the numerator, right?
Mhm.
Only difference is denominator. Can you maybe just simply plug the answer out of A into this formula for numerator and
Mhm.
then just calculate the denominator and then tell me how much you got? As I said, that this is same as number A, numerator.
I got 2.01 kilograms.
Okay, good, nice. All right, let's move on. The problem 57. Please read this problem, and I'll just start solve it.
A cylindrical tank with a large diameter is filled with water to a depth of 0.30 meters. A hole of cross-sectional area of 6.5 centimeters squared in the bottom of the tank allows water to drain out. What is the drainage rate in cubic meters per second? At what distance below the bottom of the tank is the cross-sectional area of the stream equal to 1/2 the area of the hole?
Okay, in order to solve this problem, you need the Bernoulli equation. Do you remember that the basic form of Bernoulli equation?
No.
Okay, so let me just write down. You want to just memorize. I mean, I'm pretty sure that your school provide that the basic formula, but it's just better than nothing, right? It's just always helpful to memorize basic formula. So Bernoulli equation. I already um, covered this topic and this equation, but this one, if you look at the two different spot and along the the path of the fluid with the different radius and the different speed of the liquid, then their pressure plus, so basically this same as conservation energy law. So you have pressure plus um, kinetic energy V1 squared density times the velocity of the fluid passing through that point 1 squared, the same as potential energy low G H1. That total energy should be same as pressure plus 1 over 2 low V2 square, and that is velocity. That's not volume. Just make sure that that V is actually velocity of the fluid at that spot and low H2. So now you're looking at two spots at the one place to the other, something like this. So that you have one spot point to 1 and the other spot point to 2, and that this one is H1 and this one is H2. Their relative position with respect to the reference point. And when this fluid passing through this point A, the velocity V1, and their velocity as v2 at point 2. So this is basic formula of the Bernoulli equation. So it's just indicating that the pressure and velocity and their position should be expressed in different position. Their net value should be conserved. Okay, that is basic concept, basic idea of how Bernoulli equation actually justify. So with that idea, just keep in mind that this is conserved quantity, so that should be reserved in any spot. So now with that idea, let's take a look at this water container. Now you have water container, cylindrical tank, and with the radius r, with the depth d. So depth of this water, the cylindrical tank has depth d. And there's drain hole in the middle of this bottom of this tank. And the cross section A is actually this whole thing. A is 6.5 square meter, right? The bottom of the tank. And that drain hole, you can set up the new variable, which is the outlet of this drain hole is A2. And while that's fluid drain out of this hole, the size of the cross-sectional area of this fluid will change along the fluid actually drain along this pipe. So that's this bottom of this, the cylindrical tank could be H2, and the top of this water tank could be H1. So obviously H1 minus H2 must be the D, depth of the tank, right? Because that's the relative difference. So now if you look back the Bernoulli equation, so point A, P1, let's just assume there's no pressure existing top and bottom, then that pressure at the top and bottom, they're same, only have like this relative kinetic energy term and the potential term. So with that idea, that's when this top of water, that fluid drain out of the hole, there's no velocity on the top of this tank, but bottom of tank should have some amount of variation of the velocity. So you can express this one with this condition, P1 and P2 equals 0, and the V1 also equal 0. And the V2 must be the velocity when this fluid actually drain out of this hole. All right. So with that idea, this equation could be re-expressed with a low G H1 equals 1 over 2 low V2 squared plus low G H2. All right. So now low and low could be out of this formula because all three terms have low that cancel out of this equation. So you move that H to the left-hand side, that should be G, H1 minus G, H2 is 1 over 2 V, the V2 squared. So you re-express the V2 in terms of H1 and H2, then velocity at the bottom of the tank along the hole, rain hole is 2 square root of 2G times H1 minus H2. Okay? So if you plug that H1 and H2 and G, then velocity at the bottom of the tank, at the entrance of that this drain hole should be 2 times 9.8 meter per second square, and the depth of D H minus H2 is same as D, so that is 0.3 meter. You plug that all, then the velocity at the bottom of the tank is approximately 2.42 meter per second. You find out the velocity at drain hole. Uh, so that now you know that the velocity at the bottom, and oh, actually, this one there was something wrong. That A2 is not a total A, and the 6 point, not is a 6.2. Actually, A2 itself, I gotta just probably explain. This is not A2, I just misunderstood. So that this cross-sectional area is actually A2 is 6.2. I mean 6.5 uh, square centimeter, actually the square centimeter. Okay. So now the drainage rate in the cubic meters per second is normally the area cross-sectional times the velocity. Okay, so now you have to multiply cross-section area of this drain hole to the velocity I just derived. So that is 6.5 square centimeter times 2.42 meter per second, but you have to convert this centimeter unit to the meter unit. So that is 6.5 times 1.01 meter square, right? So 1 centimeter is like one of the 100 meter, 100 meters. So you plug that, then that 2.42 meter per second. Then this one is 6.5 squared times 10 to the minus 4 meter squared times 2.42 meter per second. That is 1.6 times 10 to the minus 3 cubic meter over second. So it shows you how much amount of the fluid actually drain out of this. I mean, drain out of this cylindrical tank through this drain holes per second. Okay. Basically, you can think of this one as just cylinder right here, and this is cross section, and it is the length L, and you divide by the length L with the time. That's velocity. That's why you need to multiply the cross sectional area to the velocity, because that is same as A times V is A times length L over T, right? And A times L is volume, and that volume ratio in volume ratio per second in draining. Okay. So number B, at what distance below the bottom of the tank is cross-sectional area of this stream equal to the 1/2 the area of the hole? So same thing, you have to apply the same cross-sectional volumetric draining ratio to the entrance of the drain hole to and the okay. Yes, so that you have to just apply the same volumetric draining ratio, so in time. So if you do that, I gotta just remove this part of this one. Just a little bit. Just leave it. So here, the V3, the velocity um, at the distance, some distance from the bottom of the tank is V3. You just kind of assume. So the A3 times V3 must be same as the A2 times V2. So amount of the change of volume of fluid along this bottom of tank drain hole is same as the variation of the volume at some distance from the hole, right? Because whatever you just drain through this hole, that should be must be same as the bottom of this drain pipe. Okay, the variation itself should be conserved. The amount of variation of the fluid in time must be same. So the A3 cross-sectional area should be expressed with the uh, A2, A, oh, actually, this is the velocity. Velocity V3 be A2 divided by A3 times V2, right? So it says, what did it say? The bottom tank cross-sectional area stream equal to 1/2 the area of the hole. So that should be about 2V2, because that is twice, A2 is twice bigger than that the area of the point position 3. So that is 2 times what's the velocity? 2.42. So find 2.42. So that's 4.84 meter per second. So when this water is reached that point 3, then that speed is 4.84 meter per second. Water is free fall, and it need to find out how far it has fallen when its speed is double to the 4.84 meter per second. So that height also could be given by the Bernoulli equation. So that is 1/2 low V2 squared plus low GH2 is the same as 1/2 low V3 squared plus low GH3. So that is H3. You just introduce the new variable to find out the distance between the H2 and H3, right? There's kinetic energy plus potential energy should be conserved along those two spots. So now you can get rid of the low out of this formula. And this H2 minus H3 is distance from the bottom of this tank to the point 3, which has the area of 1/2 the area of the hole, right? So if you plug that, then now H2 minus H3, you move this second term to the left-hand side and move the 1/2 V2 squared to the right-hand side, then that should be 1/2 V3 squared minus 1/2 V2 squared times 1/g, because that you should divide by g. So that is V3 squared minus V2 squared over 2g. So you plug the numbers out of this, the answers from problem A, And problem B, then you should be able to find that the distance between the bottom of the tank to the point 3. So V3 is 4.84. V2 is, how much is it, V2? 2.42. 2.42, half of that the velocity. And you plug 9.8 meter per second in numerator. I mean the denominator. And can you tell me how far that water falls down
Mm-hmm.
it to reach the velocity? I mean, yeah, twice the velocity, the bottom of the drain hole.
Mm-hmm. I got 0.896.
Okay, that's correct. 0.896, so it's about 0.9 meter. All right, that's good. Any question?
No.
Okay, then move on to the next one. You still need to use Bernoulli equation to solve this problem too, I believe. So can you read this problem?
Mm-hmm. Water flows through a horizontal pipe, then out into the atmosphere at a speed of 15 meters per second. The diameters of the left and right sections of the pipe are 5 centimeters and 3 centimeters. What volume of water flows into the atmosphere during a 10-minute period? If the left section of the pipe, um, in the left section of the pipe, what are the speed, V2, and the gauge pressure?
So by the way, the reason I didn't take into account the pressure part in Bernoulli equation is because the points when you consider that the velocity and the height in the Bernoulli equation, um, all the spot in previous problem, they experience same amount of atmospheric pressure. So P1, P2 is same as P naught. So you don't have to worry about the pressure part. But now this is a horizontal case. So if you stay in the different spot along the horizontal streamline, then you should actually consider different amount of pressure because that is not point one and point two does not have to have the same pressure if they have different spot, different position. Okay, all right. So let's take a look. So now the water they actually just flows through the horizontal pipe and then out into the atmosphere at speed 15 meter per second. So the pipe size of the pipe varies along the streamline of this pipe. So you just have to consider variation of velocity of the water as well as the cross-sectional area too. So the first one is what volume of the water flows into the atmosphere during the 10-meter period. So the total volume of water for 10-meter, I mean 10 minutes is basically the same as the horizontal in a cylindrical horizontally actually align the cylinder. So you have cross-sectional area, A1, and the water travel distance L. Then along this distance, if the water flows with the velocity v, then the L should be same as L1 should be same as V1 times T, right?
Mhm.
So if you plug that into the this volume, so total volume of V is V1 is A1 times the L1, right? And replace L1 with the V1 times T, then A1 times L1 times T. You plug the V1, so that water for 10 minutes should be V1T times cross-sectional area A1. So here, the V1, how much is that? 15 meter per second, right? So 15 meter per second. And the 10 minute, right? That's 10 minute, 10 minute. And you got to just unit conversion from minute to second. So you apply the unit conversion, which is 60 seconds per minute. And now also the area, cross-sectional area, A1. The pipe at position A, this position is what? 3 centimeters, right? So the area is pi r squared. So the r is 0.03 meter. You plug that, and that should be 6.4 cubic meter or meter cube, right? So now that is volumetric change at the 10-minute period. So that amount of water exit at this point B out of this bottle, like the bottle of this water pipe. And now problem B is we got to find the speed of V2 and gauge pressure. So the V2, the volumetric change at the point 1 outlet and point 2 inlet must be same. So the total amount of volume change in a given unit time must be changed at outlet and inlet. So with that idea, A2 times V2 should be same as A1 times V1, right?
Mhm.
With that, the velocity V2 is expressed with the V1 times areal change, A1 over A2. All right, so now the V1 is 6.4. Oh, sorry, 15 meter per second, right? 15 meter per second. And areal change is, you don't have to just calculate the, cross-sectional area because it's ratio between the two areas. So all you need is just compare their diameter or radius and square it. So that is 3 centimeter at position 1 and the 5 centimeter diameter in position 2. All you need is just square it. Multiply it to 15 meter per second. So that is 5.4 meter per second. That is the velocity of water when it actually flows along the point 2.
Mhm.
Okay, now we got to apply the Bernoulli equation to find out the gauge pressure. Gauge pressure is net pressure above the atmospheric pressure. So based on the Bernoulli equation, which is the P1 plus 102, the kinetic energy of the water plus potential energy of the water at position 1, the same as pressure at the position 2 plus kinetic energy water at position 2 and the potential energy of water at position 2. That is Bernoulli equation. Now, as you know, H1 and H2 same, right? As you can see, they're sitting perfectly horizontal streamline. So their relative height out of the reference must be same. So H1 and H2, they are same. And here, P1, you can think of the P1 is atmospheric pressure. So if you convert it, the P2, because the cross-sectional area is different, that gauge pressure at position and at position 2 must be different, because when the water or liquid squeeze into the narrow pipe, that increases speed and also increases pressure. But the atmospheric pressure, they apply the same, equally applied to the same spot as long as they're sitting on the same horizontal line. But the pipe itself change their size, their pressure, and the speed is changed, because the total energy must be conserved. So P2 could be expressed with the atmospheric, now is P1 replaced by the P naught atmospheric pressure plus 1 over 2 low V1 square minus V2 square out of this formula by this constraint. One more time. This formula, standard Bernoulli equation, can be converted to this expression by this constraint. Understand, right? Okay, right now, the P naught is atmospheric pressure, which is about 1.01 times 10 to the 5 Pascal plus 1 over 2 times water density is 1,000 kilogram per cubic meter times initial velocity is 15 meter per second square minus the terminal velocity at points. I'm sorry, that actually position 1 is terminal velocity, and the initial velocity is 5.4 meter per second. You square it and plug the numbers into this formula, then that should be 1.99 times 10 to the 5 Pascal. That is same as 1.9, about 93 atm. So in order to find the gauge pressure, you have to just subtract atmospheric pressure of 1 atm out of this number. So the gauge pressure is 97 atm minus the 1 atm of atmospheric pressure. So that is 0.97 atm, which is 9.8 times 10 to the 4 Pascal. Okay. If you want this is like actually solution with the extra complexity. Actually, if you move this one to this side, the left-hand side, and only you need to actually calculate this term, that should be atmospheric, gauge pressure too. But I just give you just kind of like a step-by-step procedure to explain some conceptual idea how the gauge pressure is estimated general procedure. But as I said, the P naught is atmospheric pressure. If you move this P naught to the left-hand side, the P2 minus P naught itself is just is already actually gauge pressure. Okay.